it sounds like basically everybody is instead going to take the test tomorrow, which is fine. In many ways it worked better with the 2-hour late delay and stuff like that. I am in the process of finalizing the test right now. I did some looking at the best practices for this test. It said that you should aim for, it gave me a pretty big range. It said 50 to 100 multiple choice questions. In the current version, it was originally 75. I got it knocked down. I think it's at 62 or something right now. 62 multiple choice questions. And then there's 2 that are like sketch A or write a short thing, whatever, about, or whatever. So it's a pretty big test. And so make sure that you get chances to study and so on. And alright, so the test then will be tomorrow. And like I said, I will do everything I can to get it finished. Whatever. Any questions you have all those review materials. Like that review sheet, every single PowerPoint, every single exit ticket, anything that could be useful, you've got. Alright, we're moving into the second module in the class now, which is the module about forces within the Earth. Particularly it's going to be like volcanoes and earthquakes and stuff like that. We're starting with the stuff about plate tectonics. For tomorrow, you do have a short, very short prep assignment for tomorrow. And it is just about, it's either 4 or 5 pages at the beginning of chapter 4. That's just kind of like how we got here. How did we discover the whole business of plate tectonics? And you're going to learn about the interesting story of Alfred Wegener, a meteorologist of all things, who discovered continental drift. And you'll learn about how he got there and stuff like that, and what was right and what was wrong about his ideas and so on. It's a total of like 4 pages with lots of pretty pictures, right? It's not going to be huge. Then there's just like always, there should already be there on Classroom, but I'll make sure there is. You get, you answer a couple quick questions and stuff like that, okay? So that's sections 4.1 and 4.2, if I'm not mistaken. It actually takes the book surprisingly that to get there. But basically what we're doing here is we're moving into the second module. We're going to start with plate tectonics. We're going to move on and talk about earthquakes. We're going to talk about volcanoes. We're going to talk about mountain building. Hello. If we actually take a look here real quick here, this chapter 4, if you looked at the table of contents, looks a little bit like a mess because it has so many sections. None of the other chapters have so many sections. But if you actually start flipping through it, each one is tiny. Each one's like 2 pages or something like that. So even though it's all busted up into all these little pieces here, I mean, these first 2 are what you're doing in the prep assignment, which is literally like 4 or 5 pages total, where you basically just start, well, here, let me give you the actual goals here. It says you got to summarize the view that geologists held prior to the 1960s about how the continents were, where they are, and how they moved and stuff like that. And then you need to be able to, the second part, explain the evidence that Wegener presented in order to support his continental drift hypothesis. Wegener's a really interesting guy. You even get to learn in the book about how he was found dead on an ice sheet in Greenland, which sounds like something out of the X-Files or something like that. But anyway, it's funny because he's actually a huge person in the history of meteorology, but he also was the guy behind continental drift.
Was he like crazy?
No, he was brilliant.
I
don't know. Are crazy people brilliant? Are brilliant people crazy? I don't know. He was. I don't know. No, but he was out there. He was doing something in Greenland and decided to go out into the ice sheet to go like check on some instruments or something and was found dead. It's like they had an heart attack or something in Greenland. Anyway, so today we're moving forward. We're going to do section 3.3 and 3.4, where we're going to be learning about just the basics of plate tectonics and seafloor spreading. And so the book, again, because, man, I can't even emphasize enough, these goals really do tell you what kind of things are going to be asked on the test, right? These goals are the goals that are from the, and again, I provided you with that document for Module 2 that has a list of everything EVSC says they want in this class and everything Ivy Tech says they want in this class. And so for the first part of this lecture today, what they want us to do is to tell us about the major differences between 2 important layers of the Earth, the lithosphere and the asthenosphere. We'll get to those names in just a little bit, and then we're going to be explaining how they're important in the plate tectonics theory. Obviously, there were 3 big terms here. Plate tectonics is the kind of word that everybody has a vague idea about. I mean, everybody, it's the year 2019. Everybody knows continents are moving, and that's called plate tectonics, and exactly why, and exactly what tectonics means and all that kind of stuff might be a difficult part. But these other words, these little vocabulary words, point us to the fact that we actually have a little bit of thing we got to sort out. plate tectonics is the modern view about how continents are moving and why and so on, and it is more than just continental drift. Continental drift was the idea that Wegener came up with, that continents are moving, and he was very much right about that, but he had very wrong ideas too. He had thought of continents as sort of like icebergs that are plowing their way through the ocean floor and things like that. And he's very much wrong about that. But there's also, his explanation had no way of understanding why volcanoes happen, why earthquakes happen, why none of the sediments on the bottom of the ocean are all that deep, why none of the rocks on the bottom of the ocean are all that old. He had serious problems with his idea. On the other hand, he was just a meteorologist. Admittedly, a kick-ass meteorologist. But anyway, he had some very good ideas there. But he started coming up with some ideas, really even since like map makers were making maps of the world 300-400 years ago, we started noticing that there were some patterns to the continents. I mean, probably even in grade school, at some point you realize, it sure looks like South America should fit right here. Right? And it really looks like Saudi Arabia just sort of needs to move over a few inches and it would be on top of Africa, right? It doesn't take, and they fit really well, but it wasn't until we started having, in the 1960s, really good expeditions to start figuring out and map the bottom of the ocean that we started realizing there's sort of these seams that run across the whole bottom of the ocean that kind of look like the seams on a baseball, this big long continuous seam like it's being put together. And until we had that idea that we couldn't really start figuring out, I didn't realize I missed a slide here. I covered one up. Let me just see if this happens to be out of order. Nope, I made a mistake. Oh well, I'll fix it. So, before it got covered up here, it wasn't the little text that's in beige or whatever down there. It was not until the 1960s and we had like, remote pilotable submarines and things like that, that we could go and get rocks off the bottom of the ocean where it might be 4 or 5 miles down and realize that none of the rocks on the bottom of the ocean are all that old. Oh, they're millions of years old. But I mean, on a planet that's 4.7 billion years old, and frankly, we can find, more than 4 billion years old rocks in the continents, how come the ocean was so darn young? I mean, you don't find very many older than about 200 million years on the bottom of the ocean. And for that matter, none of this, once we could start drilling in the bottom of the ocean, with, oil drilling platforms and stuff, we quickly found out that the sediments weren't all that deep. That was a huge shock. I mean, we had this whole idea about sedimentary rock. We understood that before the 1960s. And the idea was, well, there's going to have been 4 billion years of sediments collected at the bottom of the ocean. It's probably going to be miles and miles deep. You're going to get to the bottom of the ocean and it's just going to be ook. That's a technical term, ook. All the way down, mud and sand and silt for miles probably. And then they discovered none of it's really all that deep.
How deep was it?
Oh, well, it depends on the rates that sediments are being deposited. Like are you close to where a river is dumping sediments into the ocean and stuff like that. Some might be as much as like a mile, but they were predicting way deeper than that. So many places it's only a matter of, hundreds of feet. They were never, how could that be? If they'd been depositing that sediment for billions of years, what was going on? As we got better at mapping the bottom of the ocean, we found all these seams in the bottom. It started becoming clear that the ocean was definitely not very old, the bottom of the ocean. Where was all this coming from? Clearly, the ocean crust is very young, and apparently it has some way of being created and some way of being destroyed. Nobody was expecting that. Somewhere rock is coming from and forming the ocean. And so, this gave us this idea that the plates were moving and being created somewhere in the ocean so that there's a source of new ocean floor at the bottom of the ocean, and somewhere it's being destroyed too. And to get to the bottom of how that would have had to be, it took a great deal of study using, drillings and boreholes and things like that, and using the vibrations from earthquakes to measure the density of different layers of the earth and so on, to discover that we had two very different things going on up near the surface of the earth. I mean, so far we haven't gotten just too bogged down on the whole crust versus mantle thing, because you all survived grade school science classes and middle school science classes. The earth has a crust and a mantle and a core, right? But you never really found out why they were different or anything like that, but we're going to learn part of the story today. But we're forgetting about crust and mantle for a moment and talking about two other layers, lithosphere and asthenosphere. The crust and the top part of the mantle, and we'll see a cross-section of this in just a little bit, but the crust and the top part of the mantle are going to make up the lithosphere. And of course, because it's farthest from the source of the heat, namely the core of the Earth, this is the coolest part. It's cool, so it has solidified and crystallized. The lithosphere is hard and strong like rock. Hence the word lithosphere. Litho means rock, like a lithographic print or something like that, which is made using stones. Underneath the lithosphere, there's a different layer with the very hard to pronounce name asthenosphere. And the asthenosphere is down a little bit lower, and it's hotter, and it's weaker. It's still a solid, but it's a solid kind of like Play-Doh, or maybe even a little thicker than that. It's not very strong. It's a solid, it's not going to get crushed, it's not a gas, or it's not a liquid that's not going to go squirting out, but it's not very strong. It's pretty easy to make it move. So I'm going to show you a cross-section here. There it goes. Here's going to be our cross-section. This is a figure from your book, showing the first, 400 kilometers or something like that in the surface of the Earth. And you can see up here near the top of the diagram, there is ocean crust, and there's continental crust. We will actually get more into the weeds about what makes ocean crust and what makes crust later. But again, you're a survivor of like grade school science and the magic school bus and all that. You know the Earth has a crust. And then, but below that, as you get into the mantle, the top part of the mantle is actually kind of crusty itself. I mean, it's pretty solid. And so, if we took a look at this top part, it might go as much as 100 kilometers down, or about 60 miles down. Which sounds like a hell of a long ways, but keep in mind, you know, all the way to the center of the Earth is a few thousand miles. This is really still a very thin little part of the top. The first 60 miles or so thick over the oceans, it's actually a little bit, oh, I didn't realize I had to zoom in here. So the first maybe 100 kilometers if we're over the ocean where it's not that deep, under the ocean rather, where it's not that deep. Or the first maybe 125 miles or so if we're talking over the land masses. It's thicker and cooler under the land masses. Is this lithosphere. It's very strong. It doesn't want to break. I mean, it doesn't want to bend. It doesn't want to flow. It's very, very strong because it's cool. It's hard. Your book makes a point of it. I'm just going to have it up here in case this comes up someplace along the way. In general, the lithosphere under the ocean is more dense than the lithosphere under the continents. That's part of the reason why the continents float. They're up higher because they're less dense, but we'll get farther into that. I have a feeling that's a point that will be emphasized better later. Oh, what happened here? Underneath that lithosphere, going from there and kind of just down as far as you want to go, I mean, it's just going to get soupier and soupier, is the asthenosphere. And the asthenosphere, remember, like clay or Play-Doh or pizza dough or something, it flows a little bit. It's actually not as flowy as like a Play-Doh or as flowy, that's not a good word, viscous, as like pizza dough, but it's pretty, it can move. It's not quite lava. It's not quite magma. It's still technically a solid. It's still not quite fully melted like you could stir it with a stick, but it is pretty close. It's definitely squishy, it can move, it can flow, especially under the weight of like mountain ranges and stuff like that. Now your book has like highlighted, and I wanted to include that too here so that you understand that. There's a big difference between these two. Although the rock in the asthenosphere is mostly solid, it responds to forces by flowing. If there's big forces, like things are happening in the magma or something like that, it can move the asthenosphere out of the way. It can, similar to the way clay may deform if you press it slowly. In contrast, the lithosphere is cold and rigid. Well, I mean, it might not be all that cold. It might even be a few hundred degrees. But it's cold enough that it's a solid. And once it's a solid, it's a solid. It's granite. And it responds to forces by acting on it by bending or breaking. We're going to do things like fold it to make mountain ranges, or snap it to make an earthquake, or punch through it to make a volcano. But we can't just make the lithosphere flow. It's gonna snap instead. It's going to bend or break. The book has a sentence here then that might be I don't want to say misleading, but might be hard to interpret right. It says that keep in mind then that the outer shell of the Earth is effectively, that lithosphere is effectively detached from the asthenosphere. I like that picture. I mean, you can take pieces of that lithosphere and slide them across. It isn't like the lithosphere is somehow attached to this asthenosphere. It can slide across it. They can move in different ways if they need to, and so on. Okay? On the other hand, the movement of what's going on in the asthenosphere will be part of why the lithosphere does what it does. But here's the deal. It is very easy to get these idea of lithosphere and asthenosphere confused with the idea of crust and mantle. And actually, there's an important idea for earth science here that's going to come up again and again, like when we do atmosphere, when we do different stuff. The lithosphere and the asthenosphere are different in the sense that they have different mechanical properties. Mechanical in the sense that they behave differently. Like, put force on one, it squishes. Put force on the other, it snaps. They are behaving differently. So we're dividing the top layer of the Earth up into these two pieces, the asthenosphere and the lithosphere, based on their mechanical property. And that is different than on the Magic School Bus or in grade school science, where you talked about the crust, the mantle, and the core, which is separating the layers based on their chemical properties. Okay? Like, there's more iron in the core, and there is more silicates in the crust, and so on, okay? So, lithosphere is the whole crust and some of the mantle. And it's just that it's hard enough and brittle enough, it's going to break. Okay? The asthenosphere is completely part of the mantle, and it's the part that's still thick enough and solid enough, it's cool enough that it's not lava, it's not splashing around or something like that, but it can move. That's an important point. Understanding that these are two different ways of dividing the first, couple hundred miles of the Earth into different layers using different properties is kind of key here as we move forward. Well, the lithosphere can break, and it does break. And in fact, it has broken into pieces called the plates, called the lithospheric plates, or just simply the plates. There is no magic here. It's just, it got cooler and it cracked. Okay? Picture, I don't know, like I know what I'm picturing. I'm picturing a raindrop freezing. When raindrops freeze as they fall, like in cold weather, they freeze from the outside, because that's the part touching the cold air, and they make a crust of ice on the outside that then starts cracking into pieces and flaking off. And but that may not be a visual that helps you. Maybe like a glob of molten glass. Can you picture like a glass blower? Okay? And as that glob, to make it a crystal ball or something, well, the outside cools first, right? And it's still gooey on the inside. Can you picture that? That is a hard outer crust, and it's soft and gooey on the inside, and then it cracks. Okay? They're just broken up into pieces, and those pieces are plates. There's no magic here. And as it happens, there's about 7 or so of them that make up just about the entirety of the Earth's surface. They're big. They're big chunks of it. And again, there's no magic here. It's just, picture a piece of glass. It just broke. Okay? The forces inside of the Earth, as the magma was churning and trying to cool and convecting and so on, it just broke. The lithosphere is broken into these pieces. And by far, if you're looking at the map here, by far the biggest one is the Pacific Plate. It doesn't look like the biggest on this stupid map. This is a stupid map projection. It's a Mercator map, and it makes the things near the North Pole look much bigger than they really are. If we had this on a better map projection or on a globe, it would be clear that nearly half the area of the Earth is the Pacific Plate. One giant plate. But there are 7 that make up almost everything. Hey, we're going to wonder what's going on over here in Africa later today, if we get that far by 1025. Anyway, look, if you're wondering, the African plate is actually breaking. Yes?
So at one time, was everything a part of the Pacific Plate?
Well, I don't know if I would ever say that. Keep in mind, this has been a process all along. I mean, we would start the Earth was forming out of planetary nebula, and then some giant damn thing would hit us, and we kind of had to start all over,
Right.
right? And then we had to start over. So I'm not really sure there's a great
'Cause I was
when we all
wondering-
started at one
I was
place.
just wondering how we ended up with like such smaller planes.
Yeah, well, there definitely have been some pieces that are broken off in weird ways, right?
Uh-huh.
Yeah. Yeah. Well, Aaron.
You said that African plate's still breaking?
Yeah.
Like fast? Like will we be able to like what do you mean?
Later today, we're going to get to, this is the African Rift Valley. There is movement under this plate. This part of Africa is moving this way, and this part's moving this way, and it's tearing open.
So it's gonna break Africa into like
Yes. Somalia and Uganda, this will be an island in the Indian Ocean a few million years from now.
That's too long.
It's much too long.
I wish it happened in a lifetime.
That's what did happen to Saudi Arabia. It was part of Africa. That's what did happen to South America and Africa. They pulled apart. They were one continent. In fact, in the lecture that you do as a prep activity for tomorrow, you're going to see there was what Pangea. Yeah.
So since North America and South America is connected, right?
Yeah.
Like barely.
Barely.
So you think there's a good chance I could break apart?
Yes, it's been broken apart before. It's just barely above sea level right now. In fact, as recently as 5 million years ago, it was open between the two. Yeah.
Oh, so they're going towards each other instead of...
There's some building about, see the Cocos Plate here? There's some mountain building happening along this spine right through here through Central
that
America
makes
right now
it like
that brought
hitting
that back
each other.
above sea level. Yeah. Yeah, we're going to learn more about the convergent plate
Like
boundaries. Yeah. And so they're driving some mountains up right now over here. But as recently as 5 billion years ago, which has a huge impact on oceanography, the Atlantic and the Pacific were connected through here, which is crazy.
Do they have maps of how it originally was before everything started?
You're going to see some, actually, not today, but like in the prep assignment. But if you go far enough back, a few odd billion years ago, it was all one big continent called Pangea, but it broke up into these pieces due to the forces that are on it. But other times, other places, they've been moving around all through human history. That's why we find things like dinosaur fossils in Antarctica. Because Antarctica hasn't always been at the South Pole. Okay? As it moves, it has been different at different latitudes. But you are right that there are, hey, by the way, one way which Wegner was wrong is he had this idea that there would be, the continents could move, but he pictured each continent was sort of like an iceberg, and it was moving through. But if you actually look at the plates, none of the plates is exactly a continent. I mean, it's actually a bunch of ocean and stuff moving with it too. But you can see how as these things move, two locations that are on the same plate, here, Evansville and New York, as they move, they stay the same distance apart, but like Evansville and Rio de Janeiro get a different distance apart, right, as the plates move around. There are, as somebody mentioned, there's a whole bunch of mid-sized plates on here too, that are probably mostly just pieces that have broken off of other plates here. There's about 7 of them or something like that. And then there's a whole bunch of microplates too, like little pieces, little faults and stuff like that along the way too. The key, of course, is that they move. Again, it's no magic. Picture, you've got a bubble bath going, okay? And you don't have like great big piles of foam here. You just sort of got little patches of foam, floating in the tub there, right? They kind of move around, they bump into each other, they swoosh into each other. You stir the tub a little bit, there's new forces acted on it, maybe this puddle of the bubbles kind of moves apart from the, tears itself apart. It's no magic. It's just a tiny thin layer of solid sitting on top of a hot liquidy ball of earth, right? And it's just moving around as the stuff underneath it moves around. Not usually fast. The continental plates move at about the speed fingernails grow. They move at about 2 inches per year. And so, but that's very real, and over geologic time, these plates have been all over the place. North America's been in the southern hemisphere at least once before, but Antarctica's been across into the northern hemisphere before. They've been moving around all over the place. They're just like little piles of bubbles in the bathtub as you stir it around. They're just floating around. But, of course, the business of what happens here is at these boundaries, right? At the edges, where one plate is touching the other, that's where things go horribly wrong. As they have to find a way to get past each other, or punch into each other, or as they're getting pulled apart from one from the other. In fact, there's a meaning to all the colors that are on here where all these boundaries are that we haven't seen yet. In fact, I've deliberately covered up with this black part of the screen. The boundaries of the business. by and large, the plates themselves are pretty stable. Not that much exciting in terms of like volcanoes and earthquakes and stuff like that happens in the middle of the plates. They're thick. The magma's way down deep, maybe 100 miles down below there. There's not much happening there. But the faults and the earthquakes and the volcanoes and stuff are all happening right here along the edges where they're rubbing against each other. And in fact, those plate boundaries can have three different types of interactions. There are divergent plate boundaries, where the plates are going in opposite directions, and something's going to have to fill in the gap in between. And there are convergent plate boundaries, where they're crunching into each other, and one's got to go down and one's got to go up. There's no place else for them to go. And there are transform plate boundaries, which is a harder word to think about. Transform means they slide past each other. And in fact, they're color-coded on this map here. Red's were the divergent, blue were the convergent, and green. And you'll see that they're kind of all over the place. Right? There's places where the ocean is divergent, it's spreading. And as it spreads, there's places where like it's sliding past. Like here, the Pacific is spreading past Antarctic, so there's a transform boundary. There's convergent boundaries where one plate is smashing into another. Here, Nazca plate is smashing into South America, building the Andes Mountains. Here is Australian Indian plate pushing north into Asia and building the Himalayas. But we're going to spend a lot of time on the second two types of boundaries in the coming days, and hopefully tomorrow. But I want to spend just a few minutes on divergent plate boundaries. The divergent plate boundaries are where the two plates are spreading apart. And in fact, well, okay, so that's where we're headed with that. We're going to have one section about each of the type of plate boundaries. And today we're only doing the first one because it's literally only like 3 paragraphs in the book. The divergent plate boundaries are what is more commonly known as seafloor spreading. The book's going to tell you you're going to need to be able to sketch or describe the movement along the divergent plate boundary. I'm going to give you a little warning about the test. Go back and look other times we've had the word sketch in the objectives, or in the the EVSC goals or the Ivy Tech goals, because that's really going to happen on the test. Okay. Anyway, so it says be able to describe the movement along a divergent plate boundary, and all a divergent plate boundary is the place where there's two plates. And for whatever reason, like whatever movement going on below it here, this plate is trying to head out this way, like this is the middle of the Atlantic Ocean. North America is headed off this way towards like Alaska. And this plate, which is the Eurasian plate, is headed off to the east. So along the way, there's sort of a seam where they're getting pulled apart. And where they're getting them pulled apart, it's nothing more fancy than magma. Hey, back here. Hold on. The magma is welling up in between. I mean, as you pull these apart, you're not making a gap here. Well, you're not making a deep hole. The magma's going to come up here and well into that place. And that is all it is. The magma just wells up into there and fills it in. It is not what you might be thinking of as like a hot spot. Some people know about hot spots, like Hawaii is a hot spot, where magma from below is punching through the plate to make the islands and the volcanoes of Hawaii. This isn't like that at all. The magma is just sort of saying, I guess I got to go up there. It's making a space for me. I guess I'm going to well up there. The magma's not doing the work here. The magma is just filling in the gap. So as you pull these two plates apart, magma just sort of oozes in and fills it in, and then you pull it apart farther and more magma oozes in. And so along the seam, the rock is very, very new. Let's use a better word than seam. The ocean ridge. The rocks are very new. And as you get farther and farther away from the ridge, the rocks are getting older and older because you're getting, towards rocks that are, that were part of this upwelling of magma, some number of millions of years ago. Your book gives you a couple of different synonyms for these things. A good word for this is that this is also a constructive boundary because it's creating new plate, or a spreading center. And to be honest, I don't love either of those words, and I haven't yet seen any place where they're on any of the state goals. But on the other hand, a bigger word that is both in public, the public uses it, and is definitely on the goals, a good word for this is seafloor spreading. The ocean starts spreading out as the ocean's seafloor, constructively creates new seafloor at the bottom. we have this system of ocean ridges. All around the world, this is where the boundaries between the plates under the ocean. Once we have the good mapping, I hope I didn't step on someone's computer there. These are the ocean ridges. This is where that seafloor spreading is happening. And a good question is, why the hell is that a ridge? I mean, we found these things because they sit about 2 to 3 kilometers higher than the ocean around it. It's like a mountain range that goes all the way around the world. In fact, the ocean ridges are the biggest feature on Earth. Why are they so high? Why is this place where magma is just sort of ooking out and squishing into this place, why is it higher? And the reason is actually shocking. It actually has only, where did it go here? The only reason why they're higher is because it's hot. The magma, as it wells up, is hot and less dense. So it kind of takes up more space. And as millions of years go by and that magma cools and gets pushed farther away from the ocean ridge, it cools, it contracts, and now it's not a ridge anymore. It's literally that dumb of a reason. I did not believe it when I first learned that. I was like, that can't be really what it is, but that's exactly what it is. It takes literally about 80 million years for the magma that wells up in the ocean ridge to completely cool down. Oh yeah, the top stuff that's right there touching the bottom of the ocean, the touching the whale poop at the bottom of the ocean, is cool more or less immediately. But you've got miles and miles and miles of it below there. It's going to take about 80 million years for that to cool and contract back down to the height of the ocean around it. It's literally just taller because it's warmer. It takes up more space because it has expanded as it got warmer. All right. Yeah, I told you that part already. But as I showed you before, this happens on land too. We normally think of this as a seafloor thing, but on Earth right now, there are 2 places where it is happening. We're currently tearing Africa apart by a continental plate that is becoming a divergent boundary. There are forces under Africa taking one part of Africa to the west and one part to the east, and we're tearing it in 2. That's called continental rifting. This is a volcano, I can't remember its name, that's on that rift. But if you take a look at Africa from space, well, this happens to be Google Earth, but whatever, you see that there's already a pretty good crack that's filling in, where like it has pulled apart and water has filled in the Great Lakes of East Africa. And it's just because this whole chunk is getting torn off. Somalia, Kenya, parts of Tanzania are being torn off. And in a few million years, this will open up and the ocean's going to come in here as like a bay or something like that and start connecting across all these Great Lakes and so on. And it's going to be a big old island in the middle of the Indian Ocean, 10 million years from now or something like that. Parts of California are the same way. Another big place where this is happening is Iceland, of all places. Iceland is being torn apart. But not everybody knows that this almost happened to North America. 1.1 billion years ago, the mid-continent rift system happened, where exactly the same sort of thing, northern Canada and like the northeast United States started spreading out in 2 different directions, and we started tearing North America apart. And there is a rift that runs from Lake Superior down through Nebraska and into Kansas, where there's igneous rocks, where both, magma welled up as the continent was getting torn apart, and you don't expect igneous rocks in the middle of a continent like that, and yet, this is in Thunder Bay, this happens to be a mafic silt, but it's a giant lump of igneous rock. You do not expect that in Wisconsin. How many volcanoes are in Wisconsin? Okay, but it was that's just like Mount Kilimanjaro in East Africa, okay? It was a big volcanic thing, it's just that it failed. We never quite managed to tear North America completely open so that water started coming in from Hudson's Bay and filling in towards Nebraska and so on. Eventually, whatever forces were tearing it apart at that time, whatever motions were happening, the mid-continent rift system never finished tearing. And so we here's another one. These are the dells in, this is not the dells that people usually hear about that are near Chicago where people go on vacation. This is a different set of dells. But these dells are volcanic, they're like weird rock formations and stuff like that along the Wisconsin-Minnesota border. Again, that's igneous rock. You don't expect a lot of volcanic activity in Minnesota and Iowa and places like that. And yet, here this stuff is, because 1.1 billion years ago it started tearing apart here. We started having lava flows and stuff like that in frickin' Iowa. Not what you expected in the middle of a continent like that. let's see if I can get it back here. Oh, that is the last slide of that. All right, so we can make these divergent plate boundaries. Most of the time, they're under the ocean. We're making seafloor spreading. But we do have two places actively right now on Earth, the East African Rift, and in Iceland, where they're happening on land right now, is continental rifting. And in fact, it has tried to happen in a couple places on Earth. The largest one ever is in the mid-continental rift system across Iowa and Minnesota, Wisconsin, and so on. The actual deepest part of that rift system is actually currently under Lake Superior. Lake Superior is very different than the other Great Lakes, but we'll learn about that in hydrology. All right. We are not going to do the exit ticket right this second. Hi. That's good. We're actually just about to head out to 10:25 is when they switch classes. But that's okay because you get your instructions. So I will double check. The exit ticket is on Classroom, but I think it was set to like, you have Classroom forces you to have an expiration date on those things. So you did it already?
Yeah.
All right. So I think I had it set to end at 10:30, but if it does, I'll open it back up and I'll send you guys a text to remind you to do the exit ticket. I'll put the deadline fairly far in the future because I want the other students to watch the video first and then do the exit ticket. You have that very short prep assignment for tomorrow. Again, mere minutes. Well, I mean, I doubt it'll be, whatever. And make sure you get ready for the test tomorrow. Okay? All right. Well, we did the best we could with the 45-minute class or whatever. All right? Yeah, Aaron.
So you are extending the deadline?
For the exit ticket?
Yeah.
Yeah, I'll probably make it tomorrow or something like that. Just because I want to make sure everybody has time to watch the video before they take it.
Okay.
And I realize we kind of have a lot of stuff right this exact minute. If we had taken the test today, that might have been a better plan, but it worked out better for everybody to take it tomorrow. I heard, yeah, yeah. Yeah, poor Marty. We'll get him figured out.
Is me and Jalen still taking that session?
No. Hold on just a second.